Okay, let's talk about trapezoids. We're going to describe what a trapezoid is. We're going to talk about isosceles trapezoids. And then on the next page, we'll talk about the mid-segment of a trapezoid. So here's our definition of a trapezoid. It's a quadrilateral with... Now this is trying to be exact, right? We're saying it has exactly one pair of parallel sides. That means no more, no less than the one pair. And as you can kind of look at the figure, you can determine where that's going to be. It's, top and bottom. So we call this the base, and this is also the base of the trapezoid. If you think about a triangle, we normally think of one base and maybe one height to find the area of a triangle. Here with the trapezoid, we actually have two bases. So those parallel sides are what we call the bases. So that means these other sides are called the legs. So here's a leg, here's a leg. So two bases and two legs. So when we say exactly one pair of parallel sides, we mean it's the bases are the parallel sides and the non-parallel sides are the legs. Now, it just so happens that there's a special connection with angles A and B as they're labeled here. The two on the left, angle C and D, the two on the right. These are consecutive angles, and those are consecutive interior angles because they're between parallel lines. So here's a little mini sketch of the same trapezoid, more or less. Remember that if we have parallel lines cut by a transversal, then those interior angles that are consecutive, that are touching that transversal, they're not congruent. No, they are supplementary. So A and B, those angles will add up to 180 degrees. And then also C and D, that would be the other transversal, they also add up to 180 degrees, right? So the reason is if parallel lines, then consecutive interior angles are supplementary. Now you have to be careful here. We cannot add up B and C to 180 degrees. We cannot add up A and D to 180 degrees. So this is different than, say, our parallelogram or rectangle or other special kinds of parallelograms. On those figures, you could add up any two consecutive angles. Here, we can only add up the two angles that are touching the leg of that trapezoid. All right. So now let's take a look at this special case of our, let me go one step farther. Because these two angles here are touching the base, we have a name for that. We call them base angles. All right, so those two are a pair of base angles because they're touching the base. But wait a minute, here's another base. That means we have another pair of base angles as well. So A and D are base angles. So notice that while A and D are base angles, you're not adding up those two to 180 degrees. You're adding up A and B to 180 degrees because they're touching the same leg. That's what we're seeing here in this little sketch. Now let's talk about our isosceles trapezoid. You've heard of an isosceles triangle. We can have an isosceles trapezoid as well. So if the legs, so we're talking about these segments here, if the legs of a trapezoid are congruent, so if the legs of a trapezoid are congruent, then the trapezoid is isosceles. So taking a look at the sketch on the right, again, here's the leg on the left. If that is congruent with the leg on the right, then that means you will have a line of symmetry running right down the center like that. So if you have a line of symmetry, then that means you could reflect the left side and map it onto the right side. And so that gives us certain pairs of congruences. Like, for example, if I take this left-hand shape and reflect it to the right-hand shape, that means this angle A is going to fall on angle B. Hey, that's a pair of base angles. Right? Those base angles are touching that top side, that base. So that means if a trapezoid is isosceles, then each pair of base angles is congruent. Each pair of base angles. So we've already marked the top pair on the sketch here. we want the bottom pair as well. So I'll use a double arc for angle D and C. We have two pairs of base angles, so that's why we say each pair of base angles is congruent. And this is the same idea, kind of the other way around. If a trapezoid has even one pair, a single pair of congruent base angles, then that's enough for us to conclude that the figure is going to be an isosceles trapezoid after all. And lastly, let's think about the diagonals here. There's a diagonal. There's another diagonal. They look to be the same size. Yeah, they are. A trapezoid is isosceles if, and only if, its diagonals are congruent. So let's use these properties in the figures below. Find some of these angle measures or diagonal lengths. Here's example number 1. They're drawing this picture of a table at an angle so it looks like a trapezoid. They're asking us to find these other angles, angle N, angle O, and angle P. They're only giving us one angle. At the bottom left is 65 degrees. Now the key word here is that it's isosceles, which means we have a line of symmetry. So you can reflect the left side to the right side. So if angle M, if the measure of angle M equals 65 degrees, well then that will also equal the measure of angle P. So those are both base angles and they're the same size. Now we also know that the top two will be the same size, but I don't have a number to reflect over. So instead, we're going to use a pair of consecutive angles because remember those are supplementary. So we're going to add those two together. The 65 degrees that we have from the measure of angle M plus the measure of angle N are supplementary. So when we subtract 65 from both sides, we will get a result of 115. So this is 115 in the top left corner, this is 115 in the top right corner. So in case that's hard to read, the measure of angle N equals 115, which also equals the measure of angle O. So those are your pairs. N and O are the same size, M and P are the same size. Here's example 2. Again, we have an isosceles trapezoid. And we are provided with a diagonal of length 17. So to find the length of AC, that's the other diagonal, it must also be 17 as well. So those are the two diagonals, and they're both equal to 17. Let's use those properties to determine even if we have a trapezoid or not. We'll just mark them as yes or no. Circle the trapezoids below which you can conclude are isosceles trapezoids. So we'll say yes or no, is it an isosceles trapezoid? So notice that in part A, they're marking the legs. The legs are congruent, and if the legs are congruent, then yes, it is an isosceles trapezoid. Here in part B, they're marking the base angles. They're saying we have a pair of base angles. They are congruent, so yes, we have an isosceles trapezoid. Here in part C, they're marking one base and one leg. That's not good enough. That is not going to form an isosceles trapezoid. And on the last one here, we're going to add up these lengths, so the total diagonal length is 8. 6 plus 2 is 8. So this is 8, this is 8, and we learned that if the diagonals are congruent, then yes, it is an isosceles trapezoid. So those are kind of like the first few topics of what we're talking about, identifying parts of the trapezoid, knowing which angles add up to 180 degrees, or which angles are the same in your isosceles. So now we're going to go to the inside of our trapezoid and talk about something we call the midsegment. So this is the next page. We'll get to the definition here in a moment. I want you to take a look at the picture here. We're going to diagram it up first. So, as you know, this is a base. This is a base. This is a leg on the left and a leg on the right. So find your leg And we're just going to estimate where the midpoint is. So somewhere right in the middle, exactly in the middle, that's a midpoint. And on the left leg, we will have a midpoint here as well. So I'm going to call this M and N. Now, if you connect those two midpoints, we have what we call a midsegment. It happens to be a segment that is right in the middle of the trapezoid. That's what this definition is. The midsegment of a trapezoid is a segment that connects. What does it connect? It connects our midpoints of the legs. And that's how you find where it is. Now, it turns out it has some properties as well. First of all, the midsegment of a trapezoid is parallel to the bases. So on our diagram, not only do we have the arrow symbol on the top and bottom base, but now we also place it here on the midsegment to show all three of those segments are parallel. Secondly, we can find its length. It is half. Half of what? Well, we have two bases here, so we have to consider both of them because the midsegment is going to be longer than this base, but it's shorter than that base. So we have to use both of them here. How do we figure out its length? It's half of something, but half of what? So the way we describe it is half of the sum of the bases. So we're going to take the length of the bases and sum them together. We'll add the bases together, and then half of that sum is the midsegment. So we'll write that down as a formula here in just a moment, but that's how we put it in words. So let's identify the parts on our diagram here that apply to these. So first of all, we said that the midsegment is parallel to the bases. We already marked it, but let's name it here. So segment AB is parallel to segment MN, and then segment MN is parallel to segment DC. Okay, so that's what we mean by parallel. And then this little formula here, how do you find the length of this? Here, if we're labeling that as MN, remember there's no bar here because we're talking about a value, a number. The length of MN is half. So that means we're going to divide something by 2. What are we dividing by 2? The sum. That means addition. What are we adding together? The bases. So here's a base from A to B, and here's a base from D to C. Right? So the idea is you add the bases together, you divide by 2, and that gives you the length of the midsegment. Now when you add two things and you divide by 2, what you're really doing is you're just finding the average. So it's another way of saying it's the average length of the bases. Right? So the average is you add up the number of things and you divide by that number. So we're adding up 2 lengths, so we're dividing by 2. So let's practice that here. In example 4, they're telling us that HK is the midsegment. How do we know that? Because you see the tick marks on either side of point H, so that has to be a midpoint. You see the tick marks on either side of point K, so that has to be a midpoint. So we're connecting the midpoint, so yes, it is a midsegment. Find HK. Okay, so we now know HK is the average of those 2 lengths. So HK equals, add up the bases, 6 and 18, and divide by 2. And that happens to be in centimeters in this case. So that makes sense. It should be bigger than 6, but smaller than 18, and there it is at 12. So that's easy enough if we just have numbers. It's more complicated if now we have expressions in terms of a variable like x. So we need to talk about this as well. Here's example 5. So again, start off with the formula. Here's my midsegment, which is called MN here. So MN is going to be half of something. Half of what? We're going to add up what? We're going to add up the bases. So here's a base of 6x minus 1. Here's the other base of 27. Now notice we're not really trying to find the mid-segment. We already have the mid-segment. It's given to us in the picture as 20.5. So that means we also have to plug this number in. So you have a 20.5 on the left-hand side. So there's the mid-segment is equal to adding up the bases and dividing by 2. Our goal is to solve for x. So the best way to do this is to get rid of that denominator. Let's undo that division by multiplying both sides by 2. So on the right-hand side, 2 over 2 cancels out. So now we don't have a denominator anymore. On the left-hand side, we're doubling the 20.5, and that gives us 41. Let's combine these like terms on the right-hand side. So 41 equals 6x, and negative 1 plus 27 is a positive 26. Let's move all the constant terms to the left-hand side. So I'm subtracting 26 from both sides. So we have 15 equals 6x. So lastly, divide both sides by 6 to get x by itself. And we have a decimal here of 2.5. So that can be tricky. So it's always good to practice, right? I want you to try the you-try problem down here in example 6. Here's our trapezoid. Notice they gave us the mid-segment. It's 18. We have to work backwards to try and find x. This is very similar to what we just saw in example 5. So pause the video, see if you can set up the right equation, and then we'll come back in a moment and work it out. Are you ready? Let's see if we set this up correctly. Again, notice they gave us the mid-segment length. That's the 18. So that goes by itself on the left-hand side. Here we have the base at the top, the 6x minus 1, and we are adding it with the base on the bottom, the 2x plus 9, and all of that is being divided by 2. Our very first step is to get rid of that fraction. So we're multiplying both sides by 2. So the 2's cancel out on the right. We're doubling the 18, and that's how we get the 36. So everything on the top is still there. Now we have to combine like terms. So 6x plus 2x is 8x, and a negative 1 plus 9 is a positive 8. Let's move the constant terms to the same side. I'm subtracting 8 from both sides. So now we have 28 on the left, and then divide away the 8 to get the x by itself. Your final answer there is 3.5. And we'll stop here.